questions 21 through 25 on the 2015 Grade 9 Pascal Math Contest. Each diagram shows a triangle labeled with its area. What is the correct order of the areas of these triangles? So for each of these, we've got to figure out the area. So let's start with M, which is the first one. The area, of course, will be the area of the full square, which is a 4 by 4 square. And then from that, we have to subtract these smaller triangles. So we have to subtract this one, and this one. And when we do, we will be left with the area of that triangle that they have labeled as M. So let's do that math. So that's going to be 1/2 base times height, 1 times 4, and then 1/2 base times height again, 1/2 3 times 3, and 1/2 base times height, 4 and 1. So this is going to be 16 minus 2 minus 4.5 minus 2, and that is 7.5. So that's basically what we have to do for N and P. Pretty much the same thing. So for N, again, it's going to be the full square, and then of course we have to subtract this triangle, and this triangle. And when you do, you will have this remaining, which is the area of N. So 1/2 base times height, 4 times 3, 1/2 1 times 4, and 1/2 3 times 1. So this will be 16 minus 6 minus 2 minus 1.5, and that is 6.5. And then now we have to do pretty much the exact same thing for P. And by now you get the hang of this. You're just subtracting 3 triangles. So it'll be 4 times 1 here, 1/2 2 times 4, and 1/2 times 2 times 3. And that is going to be 16 minus 2 minus 4 minus 3, and that is 7. So M is 7.5, P is 6.5, P is 7. So the correct order from smallest to largest, the smallest looks like it is N, because that's 6.5, and then next is P, and then next is M, from smallest to largest, and less than P, which is less than M. And therefore the answer to this question, number 21, is D. The chart shown gives the cost of installing carpet in 4 rectangular rooms of various sizes. The cost per square meter of installing carpet is always the same. What is the value of Z? Let's first concentrate on those numbers there. 10 times 15 times the cost, which would be dollars per square meter, is equal to $397.50. Well, that's 150 times C is 397.50. So C would be 397.50 divided by 150, and that is 2.65. And the units are dollars per square meters. Okay. So that's the first step. Now let's concentrate on a different set of numbers. Those numbers are these guys right here. This one and this one. So from that, we get that 15 times Y times the cost is equal to 675.75. Well, 15Y, the cost we just figured out was 2.65. So we got 675.75. And then now we can just divide through here. to get y. And when you do, you get y is equal to 17. Now we're going to look at a different set of numbers. We're going to look at this 10, this x, and this 742. From that, we get that 10x times c is equal to 742. Well, c we know is 2.65. So again, as before, divide through to solve for x. And when you do, you get x is equal to 28. And now finally we can approach these numbers right here. That one basically says that xy, which will be the dimensions, length and width, times c, cost, is equal to z. Well, x is 28, y is 17, c is 2.65. And that will allow us to solve for z. And when you multiply those out, you get 1261.40. And therefore, number 22, the answer is E. How many triples A, B, C of positive integers satisfy the condition 6ab equals c squared and a is less than b is less than c is less than or equal to 35? 6ab is equal to c squared. So basically what that means is that c squared has to be divisible by 6. So what I'm going to do is make a little table, and off we go. So I've got A, B, and C. Now, as previously mentioned, C has to be divisible by 6. So the only values I can really put are obviously less than or equal to 35 and greater than 0 because they're all positive integers, but they've got to be multiples of 6. So I can put 30, 24, let's see what else, 18, and 12 and 6. All right, so let's work with this here. Now, for each of these, I've got to figure out what is A and B. So let's take it one step at a time. Let's start with 30. When C is 30, I've got 6AB is equal to 30. 30 squared, that is. Solving for AB here, we get AB is equal to 150. So now I've got to figure out what is A and B with the condition that A has to be less than B. It makes it a little bit easier if I break it up into prime factors. 5 times 5 times 3 times 2. It helps me out a little bit. And from that, I will be able to get 25 and 6. Those two will work. And 15 and 10. So I'll write that over here, 15 and 10. These will be two triples that satisfy all the conditions of the question. All right, so in a very similar way, we have to do this for all the others. So let's move to 24. This time 6AB is equal to 24 squared. So that means AB is equal to 96. 96 in its prime factorization is 2 to the power of 5 times 3. So now we have to figure out how to make A and B so that A is less than B. And A times B is 96. 16 and 6, that would be one possible way of doing it. And 12 and 8. Because remember, A has to be less than B. Okay, we got two more. Now let's do the same thing with 18. 6AB is equal to 18 squared. Solving, we get AB is equal to 54. And 54 in terms of its prime factors is 2 times 3 to the power of 3. So 9 and 6 are the only ways to make that work. Now let's use C equal to 12. So 6AB is 12 squared. That means AB is 24. 24 in terms of its prime factors is 2 to the power 3 times 3. And I think the only way to do this would be 8 and 3 and 6 and 4 for 12 being C. And then finally we've got 6AB is equal to 6 squared. So that means AB is equal to 6. AB is 2 times 3. And therefore the only way is 2 and 3 for A and B. So how many did I get? I got 8. And therefore number 23, the answer is B. Paula, Quinn, Rufus, and Sarah are suspects in a crime. The police found links between exactly 4 pairs of suspects, Paula and Quinn, Quinn and Rufus, Rufus and Paula, Quinn and Sarah. These links can be shown in a diagram by drawing a point to represent each suspect in a line or curve, joining 2 points whenever the 2 corresponding suspects are linked. An example of a drawing that represents this information is right here. Ali, Bob, Kai, Dee, Eve, and Faye are suspects in a second crime. The police found links between exactly 8 pairs of suspects. Ali and Bob, Bob and Kai, Kai and Dee, Dee and Eve, Eve and Faye, Faye and Ali, Ali and Dee, Bob and Eve. For how many of the following drawings can the 6 dots be labeled with the names of the 6 suspects so that each of the 8 links given is represented by a line or curve in that drawing? All right, let's work on this one step at a time. So let's first start with this guy here. And let's see what happens. So we've got 1, 2, 3, 4, 5, 6. And we'll just call them A, B, C, D, E, and F. I'm not sure if that's the order, but let's see what happens. Okay, so first of all of these links, let's abbreviate them. So AB, that's one link, and so on. BC, CD, DE, EF, FA, AD, and BE. These are basically these just written out in terms of the first letter of the names, right? That's all I did there. Okay, so I've got to make sure that these links match here. Okay, AB, that's good. BC is good. CD, DE, EF, okay, we're doing well. FA, great. AD, from there to there. And BE. Okay, so you think, well, great, everything works out. But here's the thing. Other connections are present that shouldn't be present. For example, F is connected to D, but there is no FD in here. The only time there's going to be a connection or should be a connection is when there's a link between 2 suspects. If F is connected to D on this graph, it should be listed here, but F and D, who are Faye and D are not linked as suspects. So this graph, although it seems that it works out, yes, it does work out for these, but it also has extra links that are not present in, I guess, the police investigation. So that means this one, no good. So I think that's a little tricky, but I hope you get the hang of that. Okay, so now let's go to the next one. This is our square here. So we got a square, and then we've got some lines like this, like that, and then we've got one sort of connection there. Okay, let's start. I have no idea how these go, so I'm just going to write it in based on what I think could be A, B, C, D, E, F. Okay. Now let's start. A, B. Again, I'm going to be looking at those 8. AB, okay, that's great. BC works. CD, DE, EF, FA, AD, and BE, yeah, BE. So all of those are there. Now, the key thing, just like with the first one, is are there any extras? If there's any extras, this is no good. And as far as I can see, there's no extras. So what I need is there, and there's nothing additional. So that means this is great. That works out perfectly. All right. So now let's get rid of this guy here, since that is useless for us. And let's draw in the next one. So the next one is some sort of an egg shape here, I guess. And they've got two straight lines coming down like that. Okay, so let's play with this now. Let's label this. Again, I don't know, so I'm just going to write what I think: A, B, C, D, E, and F. Okay, again, going back to here, let's see. A joins to B, yep. B to C, C to D. Oh, C doesn't join to D. Actually, it does if you keep going, right? Yeah, if you keep going, it does, so that's good. DE, yeah, D to E right there. E to F. Yeah, if you keep going along that curve, it'll get to F. F to A, right, directly. A to D, down that line. And B to E, down that line. Okay, perfect. You think, okay, well, that all works out. But again, you have to see, are there any extras? And I think there's a lot of extras in this one. Because if you keep going, for example, from F all the way around to C, there's a connection, right, between F and C on the diagram. But in here, there's no FC, right? There's no FC link. So just based on that one FC, I can illustrate that there's more connections here than I have here. So this is no good. All right, so I hope you're getting the hang of this. Now let's go to the next one here. We've got these kinds of zigzags in this one. So we've got a connection here, 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 and then we've got one sort of loop around that goes all the way from here to sort of here, I guess. Okay, let's label this, see what we can do. I'm going to put A here because A's got to link up to B and F and D. So I put B here, D here, and F based on what's here. That'll allow me to make this work. And then D links to E, and then that means this has got to be C. Okay. Again, going back to my 8 links. A, B. A joins with B. B to C. Yep. C to D. D to E. Yes. E to F. F to A. A to D. And B to E. Yes, it all works out. Now, of course, as before, I have to see, are there any extra links in here? If the answer is yes, then this is no good. And looking through this, there are no extra links. I'm trying to see if there are. Everything that needs to be there is there and nothing more. So that means this is good. Okay, we're down to our last one. And the last one is a triangle. And we've got one down the middle. And it looks like we've got this sort of connection from this guy to this guy. Okay, let's label this and see what happens. I'm not really sure how to label this. The only thing I can think of is A's got to join with B, F, and D. So I've got to put A somewhere that it joins with B. So I'll put A here, and I can put B, F, and D here. Okay, let's work with this. And then C and D, or C and E are the only ones remaining, so I'll just put them there and there. Okay, A joins to B, B to C, okay, C to D, yeah, if you go straight like that, D to E, yes, E to F, yeah, if you go straight there, F to A, right there, A to D, right there, and B to E. Perfect. But as always, are there any extra links? And there's one link that's just screaming out at you right there, that curve, F to D. There is no F to D here, as you can see, right? And some people might say, wow, but this is not the only arrangement. You could put A, B, and C in another arrangement, and I encourage you to do that, as you can, to see if you can get a situation where only these are represented in the diagram. And for this one, the answer is no. So this is no good. So of those 5, these are the only 2 for which you can match it exactly, and therefore the answer is 2 for number 24, which would be B. The first 4 rows of a table with columns V, W, X, Y, and Z are shown. For each row, whenever an integer n appears in column V, column W contains the integer 2n plus 1. Column X contains 3n plus 1, Y contains 5n plus 1, and Z 7n plus 1. For every row after the first, the number in column V is the smallest positive integer that does not yet appear in any previous row. The integer 2731 appears in column W. The complete list of columns in which 2731 appears is. Alright, so the first thing I'm going to do is extrapolate this a little bit. I'm going to extend this and see what happens. Alright, so let's get the hang of this. Let's see what's happening here. So, as they explained, when you're going from V to W, you basically are doing a 2n plus 1. And then when you're going from V to X, you're doing a 3n plus 1. Right? And then from V to Y is 5n plus 1. And finally, from V to Z is a 7n plus 1. So basically, if you write it out, it would just be as follows. N would be here, and then this would be 2n plus 1, 3n plus 1, 5n plus 1, and 7n plus 1, like that. So based on that, let's figure out a few more lines, not too many, just about 3 or 4 more lines. Now, the key thing is here. What do I put there? As they explained, every row after the first, the number in column V is the smallest positive integer that does not appear yet in any previous row. So 11 seems to be the natural next choice, but 11 already appears there, so I can't put 11. 12 is the smallest, because 12 does not appear yet. And now to get all the other ones here, 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 and here, I just now take 12 to be my n, and then figure out 2n plus 1, 3n plus 1, and so on. And when I do that, I get 25, 37, 61, and 85. So what's the next one? Well, the next one is 13, because 13 doesn't appear anywhere in this row, this row, this row, and so on, right? And figuring out the other ones is easy. It's just 2n plus 1, 3n plus 1, and so on. So this will be 27. This will be, sorry, that will be, 27, 40, 66, and 92. Next one is 14, because 14 doesn't appear yet. 29, 43, 71, 99. Next one, 15, but no, because 15 appears there. It can't go in V if it's already appeared before. But 16 can go there. 16 hasn't arrived anywhere yet. So 33, 49, 81, and 113. Okay, so I think that's good enough. I don't need to keep going. I just wanted to illustrate how this works. Okay, so now we get into this whole 2731 business. They're saying it appears in column W. Okay, so somewhere 2731 appears in this column. All right, so if it does, that means I can easily figure out what is n. N, well, 2n plus 1 is equal to 2731, right? So that means 2n is 2730, and therefore n is equal to 1365. Okay, 1365 goes there. All right, so that is pretty much, all we can do with that one. Now they're asking us, where else does 2731 appear? Does it appear here, here, or here? Does it appear in X, Y, or Z? All right, let's see. Well, if 2731 appeared in Z, that would mean that 7n plus 1 is 2731. And if that's the case, then n would be equal to 390. If 2731 appeared in Y, then that would mean that 5n plus 1 is equal to 2731, and therefore n would be equal to 546. If 2731 appears in X, then that means that 3n plus 1 is equal to 2731, and therefore n is equal to 910. Okay, so let's see here. We have to figure out if this is possible. You might initially think, well, it seems like, 390, 546, it seems like it's going to appear in all of them, so the answer is B. But that's not necessarily true. It's only true if these actually appear in V. So if 910 actually does appear there, I'm just going to write it in there for now, but I've got to prove that it appears there. 546 and 390. And the reason I have to prove that these actually do appear in V or not is because if they appeared somewhere else, let's say 390 appeared here, then it cannot appear here. As the rule states right here, for every row after the first, the number in column V is the smallest positive integer that does not yet appear in the previous row. If it has already appeared, if that number has already appeared somewhere in previous rows, it can never appear in a column V after that row. Okay, so here we go. Let's just start with the 390. So I've got to show whether or not this 390 appears in any of these rows. So does 390 appear in W? If it does, it would be of the form 2n plus 1. If 390 appears in the other row, it would be of the form 3n plus 1. If it appears in Y, it would be of the form 5n plus 1. And if it appeared in Z somewhere, it would be 7n plus 1. When you solve for these, you get n is equal to 194.5. This gives you 129.6. This gives you n is equal to 77.8. This gives you 55.5. So what that means is that since these are not integers, this 390 is never going to appear in W, X, Y, or Z because it's never of any of these forms because n has to be an integer and none of these n's are integers. So that means that 390 does indeed appear here. So that is exactly what we needed. And since 390 appears there, the 7n plus 1 form of it is 2731. So 2731 does indeed appear in Z. So we can eliminate this as one of the answer choices, because we've proven that it appears in Z, and we were already told that it appears in W. All right, so I hope you get the hang of this. So now we got to move forward to 546, this guy right here. Same sort of story, same sort of scenario. Okay, so 546. If 546 is to appear in column V, what that means is that it can never have appeared anywhere in W, X, Y, or Z in any of the previous rows. So that means we have to figure out if 546 appeared earlier, yes or no. Okay, so first thing we need to do is figure out whether or not these can give integer values, yes or no. So equate these. 546 is equal to all of these, 7n plus 1. So if I do the math here, n is equal to 272.5. This gives me n is equal to 181.6. This gives me n is equal to 109, exactly, an integer, great. And this is 77.85. Okay, so all of these didn't work except this one right here. Okay, so 109 is sort of my potential. I'm not sure, though, if 109 will appear, but it could. If 109 appears there, then the 5n plus 1 would be 546. But if 546 appears there, then it can't appear here. So I've got to retrace my steps. I've got to first concentrate on if 109 appears there or not. So we got a little bit of double work now. Okay, so let's go through this. We have to now do the same thing for 109. Does it equal 2n plus 1 and so on? 3n plus 1, 109, 5n plus 1, 109, 7n plus 1. Okay, for each of these we get the following. N here is 54 exactly, n here is 36 exactly, n here is 21.6, and n here is 15.4 approximately. Okay, let's just concentrate on the 54. We'll put in both integers, 36 and 54. 54. Okay, well, we got to do the same thing with 54, so we got a lot of work here. 54, same thing. Well, you get the hang of it. I'm going to do pretty much the same thing there. Can it equal 2n plus 1, 3n plus 1, 5n plus 1, and 7n plus 1? And when I do that, I get values of n of 26.5, 17.6, 10.6, and 7.5. So since none of those are integers, that means that 54 cannot appear in W, X, Y, or Z, because the starting point has to be an integer, the starting point being n in column V. And since the starting point is not an integer, 54 can never appear in W, X, Y, or Z. So 54 can appear in column V. So I will put a check mark right here. So this is valid. If 54 can appear there, which it can, I've proven that, then that means the 2n plus 1 is 109. Right? And that means that 109 cannot appear here. Since 109 has already appeared there, it cannot appear later on. So that is not allowed. And since 109 cannot appear there, we will not get a 546 there. And since 546 cannot appear there, it can appear here. Right? And since 546 can appear there, when we do the 5n plus 1, it will end up creating a 2731 here. So it also appears in column Y. So I guess we can eliminate this one and this one. Now we just have to show, does it appear in X? Yes or no? The 2731. All right, so if it's going to appear in X, that's 3n plus 1. That means we've got to look at this guy here, 910. So we've got to concentrate on this guy now. If 910 appears in any of the others, then it cannot appear here. So let's see if it could appear in any of the other columns. So 910 would equal either 2n plus 1, or 910 would equal 3n plus 1, or it would equal 5n plus 1, or it would equal 7n plus 1. For each of these, when we solve for n, we get the following: 454.5, 303 exactly, an integer, 181.8, and 129.8 approximately. So the only one that gives an integer value is 303. All right, so let's concentrate on the 303. 303. Now, I'm not sure if it will appear in V or not, but let's see. If it appears in V, that means it does not appear anywhere previously. So we have to see 303, can it equal 2n plus 1, and so on. 3n plus 1, 5n plus 1, 7n plus 1. All right, so for each of these we solve, and let's see what we get. For the first one, we get exactly 151. And then the next one we get 100.6. The next one is 60.4. And the next one is 43.1. All right, so we get another integer value, 151. Okay. So I've got to figure out if 151 can appear there. So I got to go through this whole thing again. All right. By this point, you become an expert, so you don't need me to talk you through it anymore. We got to, again, equate these 4 to 151. And when I do, I get the following values for n. I get 75 exactly. I get 50 exactly. I get 30 exactly. And I get 21.4. So any one of these will be sufficient to prove whether or not 151 can go there or not. So let's just try 30. Well, 30, I'm confident that it will appear there, but let's just be 100% sure by equating them to these 4. When you do, you get n is equal to 14.5, 9.6, 5.8, and 4.1, all approximate. So that means that 30 cannot appear in W, X, Y, or Z because the starting point has to be an integer. None of these are integers. So 30 can appear here in column V. If 30 appears in column V, then the 5n plus 1 will be 151. So since 151 appears there, so now let's talk about this carefully. 30 can appear here, as I have shown. If 30 can appear there, the 151 can appear there in the Y column. If 151 appears there, it cannot therefore appear there, right? Because it's already appeared before, therefore that number cannot go in V later on. If 151 cannot appear in the V, then that means that when you take the 2n plus 1 of it and made 303, the 303 will never happen there because 151 couldn't be placed there, so you're not going to get that 303 there. So since 303 cannot go there, it can go here. It can eventually end up in the V column. If 303 ends up in the V column, then the 3n plus 1 will be a 910, which is right here. And since the 910 does indeed appear there, it cannot, therefore, appear here in the V column, since it's already been there. And therefore, if you were to do the 3n plus 1 and try to make it into 2731, there's no way it would go there. Since 910 does not appear there, the 2731 would not appear there. So that shows that it does not appear in X. So this is out, B is out, and therefore by thorough process, we have proven that the 2731 can only appear in W as they have stated in the question. We proved that it appeared in Z, and we proved that it appeared in Y, and it does not appear in X. So it appears only in W, Y, and Z, therefore number 25, the answer is D.